Welcome friends, in this one, take a look at answering this question from the 2018 AP Calculus BC question 2, that is, researchers in the border investigating plankton cells in the sea. At a depth of h meters, the density of plankton cells in millions of cells per cubic meter modeled by P of h equals 0.28 squared e to the negative 0.00258 squared, where 0 less than h less than 30 each, and is modeled by f of h for h greater than or equal to 30. The continuous function f is not explicitly given. So the first question says the following here. Find p prime of 25. What that means is you have to basically do this on your calculator. So punch it into your calculator, you're going to get the following. D, so the derivative feature on your calculator, like on the TI-89, you got to go to F3, okay? And then here you would type your P of H, comma, you're going to differentiate with respect to H. And then because you want to evaluate this at H equals 25, on most calculators, well, the TI-89, you got to put a vertical bar, you got to put H, and then assign a value like 25. You punch this in, it's going to give you the following. Negative 1.17, and then here 906. You just have to make sure you have the right units here. So the units would be million, and then cells per cubic meter per meter. These would be the units. Now let's take a look at the second one. Consider a vertical column of water in the sea with a horizontal cross-section of constant area 3 square meters. The nearest million, how many plankton cells are in this column of water between h equals 0 and h equals 30 meters? So let's first make sure we understand the concept of this column of water. So maybe a cross-section is a circle, and maybe this one is also a circle. And a column of water is something that kind of looks like this, right here. Then what you can do here is the following, right? Like the height of this would be 30 meters, like this. So this is, say, 30 meters. And the cross-sectional area is 3 meters. So on the bottom, you could, for example, put 3 meters and then squared. And then take a look at what happens when I multiply all the units together. So I'm going to have the following here. Meters squared from the bottom, times, and then on top here I'm going to have million and then cells, and on the bottom it's density, so it's going to be per meter cubed, and then you're going to multiply by the height of this water over here. So for now I'll just put the units in there, which would be meters. I multiply all of these together, and the thing that remains is million cells. So what this means is to actually find, for example, to the nearest million, how many plankton cells are in this column of water. What I have to do is integrate. I have to proceed, in other words, this way. Integral here from 0. Next one here would be 30. And I'm going to do 3 because it's 3 meters squared, right, cross-sectional area. And then P of H. And then after that, you have to multiply by DH here. This is your integral. From here, of course, this is just calculator work. So however I choose to do it on the TI-89, you're going to have to access the integrate feature under F3 for calc. And then there you're going to have to input something like this, essentially, right? So 3 P of H, comma, and then H, comma, 0, and then 30. And then you tell the calculator to work this out for you. It's going to give you 1,675, essentially, million, and then cells. Calculator work. Let's look at the next one now. So the next one is the biggest one here. It says there's a function u such that 0 is less than f of h, which is less than u of h for all h greater than or equal to 30. This integral here of u of h from 30 to infinity is 1 to 5. The column of water in part B is k meters deep, where k is greater than 30. Write an expression involving one or more integrals that gives the number of plankton cells in millions in the entire column. Explain why the number of plankton cells in the column is less than or equal to 2,000 million. So first, let's just understand what's happening here. Again, you're going to have this column of water, like this, and then like this. Okay, this will be the size of the column of water. So like this, and then like this, pretty much. And imagine that this whole thing, this is down below here is 30, okay? And imagine here, this is 0. Imagine, remember, each cross-sectional area is 3 meters squared this way. Notice over here, remember, it says right here in this box that k is greater than 30 in red. Which means what you're going to have is something like this. You're going to integrate down to some unknown value of k beginning with 30, like this in your column of water, roughly speaking. Okay, so maybe imagine this is a k down below. Now, this part right here, we already know what that is. So that's governed by our P of H in terms of the density, right? But this part right here, well, that's governed by the following, F of H. We're told that at the beginning of the top of the problem. But this is now less than or equal to, as we are told here, look, right here in this box, okay, blue, F of H is less than or equal to U of H. So F of H would be less than or equal to U of H for this part right here. Now, what impact does this have on the integral? So you're going to integrate the first part. That's easy. From 0 to 30, And then here you're going to have 3p of h for the same reason as in the previous question up there. You're going to do dh, and then you have to add to it the integral, and that integral is going to begin at 30 and go over or down rather to k. So you're going to begin here at 30, which is where the first one leaves off, and you're going to integrate to k. And now that second one is f of h. Remember the cross-sectional area is 3. So in other words, what you would have here would be 3 f of h and then dh this way for that part. Now, having said that, remember the following. That this piece is this piece. That doesn't change, right? But this second piece, that integral, you're told that f of h is less than or equal to u of h. So I can kind of add this piece. The only difference is because f of h is less than or equal to u of h, just put u of h in this position instead. And then lastly, you also know that the following is true essentially. So less than kind of equal to, again, you're going to copy the first one and this quantity right here. The integral of 3u of h will be replaced with the integral between 30 and positive infinity of just, for example, u of h. But you're going to multiply by 3 again. So in other words, it's this part. The only difference is this here is going to be, in terms of the upper limit, positive infinity right here. So you see, right here is going to be positive infinity. We kind of know that the first peak is already, we found it to be 1675. The other one now, we found that to be 105, but because you're multiplying by 3 in this position, this red 3, it's going to be really 3 times and then 105. So when you add all of this up, this turns out to be 1990, which is certainly less than 2,000 million. So that proves the answer to the last question. Let me see what I can show you all of the work from top to bottom here. Maybe possible or not. It's going to be kind of small. Okay, maybe I can make it a bit bigger. 1 second. This is everything. This is like and subscribe. Thank you so much for watching. I'll see you in another video.